All right, in this lesson we're going to look at friction, Newton's laws 3. So we're going to look at static friction, friction in general, static friction, kinetic friction, and then static versus kinetic friction, how to know when to use one and when to use the other. And of course we have to talk about what these are. So let's talk about friction first. So friction is the force between two surfaces which impedes the sliding of one surface past the other. And so we sort of have a general idea on what friction is, but just the scientific definition here is it so if I put some object on the ground and I try to slide it across, we're saying where the surfaces are actually moving over the top of one another, not rolling on each other, but actually sliding across each other, is that it's the force between those two surfaces that always pushes backwards against the direction of motion or the direction of applied force. We could talk about friction in the case of an object that doesn't move. If I were to take, a very, very heavy desk and push on it in one direction, it doesn't move in some cases because the fact there's a frictional force opposing my force that's applied to it here. And so it always opposes the sliding of one surface past the other. And so this is what friction is. The reason why we have friction, the reason where it comes from basically forces between the electrons and protons, the atoms along the surface, primarily due to roughness as the teeth of one surface catch on the other. So if we have two surfaces here, really when you look at the surfaces, they're like microscopically, you'd sort of notice some roughness in the surface. And so if I have another surface I'm going to put on top of that, it would probably, look a little bit sort of rough like this. Obviously, it wouldn't cross over it like that. But as this surface moves this way, and then as our other surface moves this way, is these teeth in here are going to catch on one another. And so we're going to see some catching that goes on in here, and some catching that goes on in there, and some catching that goes on as this hits that. And so what's happening is that there's repulsion between those electrons. And so basically there's a force that's going to make the blue surface electrons push back on the green surface electrons, and make the green surface electrons push back on the blue surface electrons. And the same thing is going to happen in here, is that so we get these forces which are always opposing the direction of motion, and they're caused by these electrons. Even if you had very, very smooth surfaces, there still would be some frictional force, because of the fact that there are going to be pushes and pulls in electrons as they and protons as the electrons sort of move around the atom here. Sometimes you'll have a case where an electron is on the far side of an atom for one surface, but there is an electron on the near side on the other. So let's say if we have a surface right here, sometimes if we have an atom, there's a nucleus here, there's a nucleus here. Sometimes you'll end up with a situation where the electrons on one surface are up here, but the electrons on the other surface are here. When you do that, there is going to basically be an attractive force that'll go on between these two. And that attractive force is, if one object is moving in one direction and the other is moving in the other direction, is going to tend to pull things towards each other in opposed motion. And so the primary way that frictional forces happen is due to this sort of teeth issue right here, but it can be due to these electron-proton forces that go on between surfaces in some cases. So that's friction. To figure out how big it is, the magnitude of the frictional force is always directly proportional to the compressional force between the surfaces, which in 95% of the cases is going to be the normal force, or well, a large percentage of cases the normal force. In this class, it's always going to be the normal force. So if I have a surface right here and an object sitting on the surface, what will determine exactly how much frictional force there is generally going to be that normal force. If I were to lift up on this box, if I were to try to, attach, cables to it or something and lift up on it, is that as I lifted upward on the box, is that my normal force would decrease, and then if I were sliding it, my frictional force would decrease, and which we sort of have a pretty good commonsensical notion of this. If we have this heavy desk we want to move, we try to push it and it doesn't want to move very well. Common sense tells us if you lift up on the desk a little bit and try to slide it, then you should end up with it being easier to move because you have now a smaller frictional force, because it has to do with basically this compressional force, the normal force going in the upward direction, and that normal force has an equal and opposite force back on the surface going the other direction. And so that magnitude of that compressional force will determine the magnitude of the frictional force. Next statement here, the frictional force is always directed parallel to the surface. And so frictional force, if we're sliding the box in this direction, the frictional force will go in that direction here. You're never going to have an angled frictional force which goes sort of up from the surface or down into the surface. It's always parallel to the surface. Or another way to say it is it's always perpendicular to the normal force. The normal force and the frictional force are actually sort of two different sides of the same force. it's just these are the two components of it, normal and frictional. And so always perpendicular to the normal force, always parallel to the surface. And the frictional force for this class does not depend on the area of contact between the two objects. And so for in simplified form, and that's really, we can treat it this way, is there is some dependence that goes on when you really look at things in a very, very detailed fashion. But when you look at objects in general, you can treat it like you have no dependence on the area of contact or when moving on the velocity of the object. And so an object which basically has a very, very small area on it and a very, very large area, if these two objects have the same normal force going upward, they're going to have the same frictional force, all other things being equal. Is that to at least the first approximation that we're going to go through. And the same thing is true about if an object is moving, then the frictional force is independent of its velocity. And so it doesn't matter how fast it's going, you're going to see roughly the same frictional force. It doesn't matter if it's just barely moving or if it's moving and sliding at 100 miles per hour. So this basically is what we start off with friction, some general statements about friction that we can sort of treat as true. So moving on from this, let's look at static friction. And so we said before that the word static or statics means not moving. And so if we're talking about static friction, we're talking about the friction of an object that is at rest. It has a velocity of 0. If we were to take this object and we were to apply a force to it, call that the applied force right here, this will have a frictional force back in the opposite direction that will oppose that applied force, because if there wasn't a frictional force, then the object would be accelerating, and thus it would be moving, and thus it wouldn't be static, wouldn't have a velocity of 0. And so this frictional force has to oppose this applied force. So we can make a first statement here. If an object is at rest, then the frictional force is 0. And so if I left something out here. If an object is at rest with no applied force in the horizontal direction, that's a major mess up that I left out there. If an object is at rest with no applied force in the horizontal direction, the frictional force is 0. If you just have a box sitting on the ground, it has a gravitational force downward, it has a normal force upward, but there are no other forces on it, then there's also no frictional force. But if we take a small outside force, we put a small outside force applied to the object parallel to the surface, that's our frictional force, or our applied force in that direction, then a frictional force, which is the static frictional force, will exactly oppose that applied force, keeping the object still. And so in the case that we have up here, that our applied force and our frictional force right here would have to be exactly equal and in opposite directions, because if it didn't, then the object wouldn't move, or the object would move. I mean, we can sort of think about this. If you right now go and stand up and find a desk or find a table and you push on it with a very, very small force, the table does not move. And so that means that since you're applying a force to it, there has to be another force which is counter-applied to your force that's keeping that object from moving. And it has to be at the equal magnitude of the force you're applying. And so this is true about the static frictional force, is that for an object that's not moving, that has an applied force on it, that has a frictional force, that frictional force will equally oppose that applied force in the direction of the surface, parallel to the surface. Now, if you keep pushing on that table or pushing on that desk hard enough, you'll eventually see that the object will move. It's called breakaway at that point, basically where it goes from being not moving to all of a sudden start moving here. And so the outside force is great enough, the object will move, and now this frictional force is no longer static. It's what we'll call kinetic. We'll talk about that next. So as a result, we could write the static frictional force. So FF is going to be our static frictional force here, is always going to be less than or equal to mu s times Fn. And so our little, this guy right here, remember, is our mu, Greek letter for lowercase m. So that's it right there. So we have mu s times Fn, where Fn is the normal force, mu s is the coefficient of static friction, we'll talk about that in a second, and FF is the static frictional force. So, if the frictional force or the applied force is less than mu s times Fn, then the frictional force will simply be what it's needed to oppose that. And so, if I'm applying a 20 Newton force on an object and the object doesn't move, then that's me, and applying the 20 newton force horizontal to the, or parallel to the surface, then the frictional force must also be 20 newtons. But let's say that for this object that I determine that mu s times Fn, for just some example here, is equal to 100 newtons. If I were to push with 120 newtons, then the frictional force cannot be any larger than this 100 newtons. So if I'm pushing with 120 newtons, then it can't withstand it. It's going to give, and so the object's going to start moving. And so no longer do I have a static frictional force anymore. So we said before, Ff is the static frictional force. In this case, it's the force of friction. In this case, it's static. Mu s, the coefficient of static friction. The coefficient of friction, in this case static friction, mu s, is a unitless value indicating the frictional resistance of a material. Each material has its own value of mu s based on how sort of unsmooth the material is, how frictiony, to use another made-up word. So when we talk about the coefficient of friction, it's unique for different substances. And so there's some substances that have very, very small values of mu. Teflon, used to coat pans, non-stick pans, that has an incredibly low value of mu s. Very, very small coefficient of friction, and therefore if you have something that tries to slide on it, you get a very, very small frictional force. There are other objects or other substances that are going to have much larger values of the coefficient of friction. For most objects, your coefficients of friction are going to be less than 1. Not always. There are some materials that do have ones that are higher than that, but for most, that tends to be the case. And so coefficient of friction has no value, has no unit. It has a value. It has no unit, so it is unitless, so don't have to worry about putting in a unit for it. It does have a value, and that value depends on the substance you're sliding across. Okay, so this is what we got so far. So if you want to find the frictional force if something's not moving, then that frictional force will be equal to the applied force parallel to the surface, as long as that applied force isn't any greater than mu s times the normal force, the coefficient of static friction for the surface, for the substance that it's sitting on, times the normal force of the object, in this case that normal force of the object that's going upward right up here, that you're basically sliding. So this is what we've got so far for static friction. Let's take a look at our next one up, which is kinetic friction. So we've now applied a force which is great enough to get the object moving. Since the object's moving now, it's not static frictional force. There is still a frictional force. There is something pushing back against it. It's not like the frictional force just disappears in this case. If an object is moving, the frictional force is what we call kinetic frictional force. The kinetic frictional force is much simpler sort of to apply here. It's just equal to the frictional force. The kinetic frictional force is equal to mu k, which is the coefficient of kinetic friction, and I completely messed that up, so ignore that word static right there. It should be kinetic. Kinetic, and it's mu k. Sorry about that. So the kinetic frictional force is given by Ff equals mu k, this coefficient of kinetic friction, times Fn, the normal force. It's formed exactly the same way as the static frictional force. The only difference is, instead of talking about it being less than or equal to, this one's straight up just equal. The kinetic frictional force is basically, for all intents and purposes, constant with respect to speed. It doesn't make a difference how fast it's going. There is going to be some variation, once again, but that's it's more of a second order principle here, in the sense of basically when we say that, what we mean is that we can ignore it for simple cases. If you really want to get super detailed, you would find there is a dependence on velocity, but it's not an obvious dependence. And so unlike the static frictional force, which as you increase your applied force, then you see an increase in the static frictional force, the kinetic frictional force is that if you put a different applied force on it, you're going to see the same kinetic frictional force. That does not change. So mu k, the coefficient of kinetic friction, works the same way as the coefficient of static friction. It's unitless. It has a value that's usually less than 1 for most substances. We'll compare the two in just a second, kinetic versus static coefficients, and this is basically it. So let's actually compare these and see how we actually might go about using our kinetic and static frictional forces. Whoops. Let's look at static versus kinetic friction. So for a given substance, so if I have Teflon, or I have a particular type of carpet, or I have soil, soil slides, I guess, a little bit, maybe slate, some sort of rock that's going on here. For a given substance, the coefficient of static friction is larger than the coefficient of kinetic friction. And so that means you're always going to get the case where mu s is going to be greater than mu k right there. And so mu s might be 0.5 and mu k 0.3. But you're always going to have a static coefficient of static friction greater than coefficient of kinetic friction. What that means is that if everything else is equal, same normal force, same surface, all of that stuff right there, that you can get a greater frictional force possible with a stationary object than a moving object. And once again, if you think about this, this has some common sense to it. If you've ever tried to push a heavy object across a surface, you know that once you get it started going, it's easier to keep moving than it is to stop it and then restart it again. The reason why is because the coefficient of static friction is larger than the coefficient of kinetic friction, and so as a result is you can get a larger frictional force that way. It's also the reason why in your car you want to avoid skidding if you want to stop effectively, because when your wheels roll, they're basically in static friction with the ground. They don't slide over the ground if you're running your car normally. If you're just driving down or braking normally, then you basically, your car is, the bottom of the wheels are in direct contact of the ground, not sliding across it. And so as a result, the frictional force you have available to you is your static frictional force, which can be larger than your kinetic frictional force. If you start sliding, then all of a sudden the frictional force available to you, that is your stopping power, basically has dropped. And now you can't stop as effectively. You have less force that's stopping you, and so you'll typically slide farther. This is why it's important that you don't skid on ice. If you keep you keep that force static between the two objects, the static frictional force, then you're much more likely to stop more effectively. So, if we were to graph this here, if we were to graph basically applied force on an object versus frictional force, and so in this case, this graph right here is calling it time, but really what we're doing is we're increasing the applied force right here. And so as we increase the applied force and we look on this axis, the frictional force, what we'll see is that if the applied force is 0 down here, then the frictional force would be 0. That's the case we talked about with no applied force, no frictional force. As we increase the applied force, the frictional force increases. And it increases until it gets to a maximum value of the static frictional force, which we basically said is mu s times the normal force right here. It gets up to that value. And so, but once it gets to that value, once the applied force is at that height right here, then what's going to happen is this object is all of a sudden going to start moving. And once it starts moving, now it's not going to be at mu s anymore. Now it's going to be at mu k, and mu k has a lower value. And so it's now going to have a value right about in there. You can sort of see on the graph it's not quite constant, then we talked about that a little bit, but for this class we're going to treat it as it is. And so that the kinetic frictional force then is going to remain constant. As the applied force increases down here, that kinetic frictional force does not change. And so this is typically what you see. And so if you're trying to stop, is that you know that force will increase as you're going up until you get to a maximum point, then you start skidding, and now you don't have as much frictional force to stop you anymore. And so this right here would be sort of static versus kinetic friction here. So let's take a look at how we might solve some problems dealing with friction. So let's suppose that I have a 50 kilogram rock resting on a horizontal surface. It has a coefficient mu s of 0.75, mu k of 0.55 for my coefficients of friction. If a force of 250 newtons is applied parallel to the surface. That's our first part here. So let's say that we have our surface right here. We have some rock right here, which is a 50 kilogram rock. Okay, right there. And let's talk about the forces on this rock. Well, we have gravity pointing down, Fg. We have a normal force pointing up, Fn. We should have a applied force, which is over here, and we're told what that is. We're told that the applied force in this first section is 250 newtons. And we have a frictional force, which is always parallel to and in the opposite direction, parallel to the surface in the opposite direction of the applied force, or the direction of motion. So what is the frictional force on a 50 kilogram rock resting on a horizontal surface? These values, if a force of 250 newtons is applied parallel to the surface. Now, we don't know if this rock is moving or not. It's possible that this force of 250 newtons is not sufficient to make the rock move, in which case it's static friction. Or it's possible this is enough to make it start moving, in which case it's kinetic friction. Since we don't know, we want to start off with static friction first. And so to start off with static friction, we're first going to want to figure out what the normal force is. And so in this case, there are only two forces in the y direction. Those forces are the normal force upward and the gravitational force downward. They have to be equal because this rock is not accelerating upward. It's not flying into the air. It's not crashing down through the ground. It's just going to be sliding on the surface if it's sliding at all. And so that means that my normal force Fn is going to be equal to my gravitational force Fg, and the gravitational force Fg here should be equal to 9.8, the acceleration of gravity, we can assume this is on Earth, times 50. And so that means that my normal force is going to have to be equal 90.8 times 50, which should give me 490 newtons. And so that's going to be my normal force. All right. If I know that, then I know that the frictional force, if I'm talking about static, is always going to be less than or equal to mu s, which is 0.75, times the normal force, 490 newtons. And so solving this out, the frictional force of static frictional force can be at least as high as 0.75 times 490. If we put that in our calculator, we get 367.5 newtons. So that's the maximum value that our frictional force can have. Well, what's the applied force? Looking back over here, we're told that the applied force on this object is 250 newtons in this case. And so, since our applied force is smaller than the maximum possible frictional force, static frictional force, we know this object is not moving. It's stationary. And if the object is stationary, that means that the frictional force is exactly equal to the applied force. They have to be, otherwise they would cancel, otherwise they wouldn't cancel out and it would accelerate and it wouldn't be sitting still. So that means that my actual value of the frictional force is going to be less than 367.5. It will be 250 newtons because it has to equally oppose that applied force to keep it from moving. And we know it's not moving because we have not gotten to that breakaway point. We don't have enough force to get past this 367.5. Okay, so that's our first question here. Second part of the question, divide my screen in half here, it says that what about if it was at 450 newtons and not 250? And so now we're not at 250 anymore. We are at 450 newtons is our applied force. So looking at this, we say if our applied force is 450 newtons, let's look back. We started off the same way we did this one. We find that the frictional force can take a maximum value of 367.5. Our applied force, is it greater than that? Yes. We have an applied force in the x direction. It's bigger than 367.5. Since it's bigger than 367.5, we know this object will be moving. And so if it's moving, then we're not going to use the static frictional force. We're going to use the kinetic frictional force. And if we look at the kinetic frictional force, we know that's equal to mu k times the normal force. And so our kinetic frictional force would be equal to mu k. Mu k is 0.55. Times the normal force, which doesn't change here. Normal force is still 490 newtons. And so in this case right here, we do the math on this. 0.55 times 490 equals 269.5 newtons. And so significant figure-wise, it's a 50 kilogram rock. That's 1 sig fig, 2 for everything else. So our frictional force here would be right at 300, equals 300 newtons. And so that would be our rounded value right here. Because the fact that when it's kinetic, all you have to do is figure out what the frictional force is. You don't have to compare it with anything else, like you did for the static frictional force. So if we had a force of 250 newtons applied to the surface, then our frictional force would be 250 newtons. If we had a force of 450 newtons applied to the surface, our frictional force would be 300 newtons. In fact, if we didn't round it, it's 269.5. You can see actually those two are both fairly close, just by coincidence in this case. In fact, it is possible sometimes, as we said, to have a higher value for the static frictional force than for the kinetic. It's also possible to have the reverse of that, where the kinetic's higher than the static, but you just have to solve it out. Let's try another example. Let's add a little more complexity to this. Let's suppose that our applied force is not actually parallel to the surface. So now, same rock, but this time we're going to apply our 450 Newton force 10 degrees below the surface. And so sketching out our rock again, here's our surface, here's our rock. Right here, the forces on the rock are going to be that we do have an applied force down this direction. I'm going to go ahead and draw in some nice components on this. We know the angle on this is 10 degrees. This is going to be our applied force down in that direction. We also do have a gravitational force, Fg, we have a normal force upward, Fn, and we have a frictional force, which is going to oppose basically the x component of our applied force, because the one that's actually going to be making this rock move, it's going to be trying to overcome the frictional force, isn't the actual applied force, it's the x component of the applied force. That's what's pushing parallel to the surface. That's the one we're interested in. So this question asks not just what the frictional force is, it actually asks for the acceleration on the rock. And so we're going to set this up to find the net force. But to find the net force, we have to find the frictional force first. So in looking at this right here, a couple things that we can say. The first one is that, once again, in the y direction, this rock should not be flying up in the air. It should not be accelerating down through the ground. So our total force in the y direction has to be 0. And so if we were to set these up and add them up, we would say that in the positive direction, we have the normal force, Fn. And that normal force would have to be equal to, in order to cancel out so we don't have a net force in the y direction, the two forces downward. And those two forces downward are going to be the y component of the applied force. And so that's going to be, the applied force is 450 newtons times the y direction. And so we're looking at this guy right here. And so it's like FAY. And that's going to be equal to 450 times the, let's see, we're talking about opposite here, so times the sine of 10 degrees. And so if you do 450 times sine of 10 degrees, right up there, and then plus, the rest of this is going to be plus our other force in the y direction downward, which is the gravitational force, which in this case would be 50 kilograms times 9.8. We already figured that out last time. It's 490 newtons. So 490 right here. And so this would have to equal to our normal force. If we actually go ahead and solve that out, 450 times sine of 10 plus 490, we should get 568.1416 newtons is our normal force. Note that our normal force is now bigger than what it was before. Before it was just 490. Now it's 568. Why is that? We're pushing down. We're increasing that compression. The compressional force between the rock and the ground is higher now, and so as a result, we should have a higher frictional force. If you don't want someone to move something, you push down on it. You push down on it, increases the normal force, increases the frictional force, makes it harder to move. Lifting up would do the opposite of that. So that's the reason why we have a larger normal force here. Now, let's check. We don't know if this thing's accelerating at all. It might just be sitting still. And so if it is, we're going to need to take a look at the static frictional force first. And so the static frictional force is going to be less than or equal to mu s, which here is 0.75, times the normal force, which we just found was 568.14116 right here. And so that means that the static frictional force, if you do the math on this, would be less than or equal to 426.106 newtons. Now, so the question is this enough to overcome? Is our applied force greater enough to overcome and make this static? Make this kinetic? Well, our applied force is 450, so at first you might say, oh, 450 is bigger than 426. But that's actually not correct, because that 450 is angled downward. We're really only concerned with the x component of this. We really want to see what is our FAX right here. That's the one that has to be bigger than this 426. And so to find that FAX right here, we're going to have to say, okay, the applied force in the x direction would be equal to 450 times cosine of 10. When you do that, you get 443.16 newtons. And so is 443.16 bigger than the frictional force? Yes, it is. So it turns out this actually will move, because the fact that our 443 is bigger than our 426, which is the largest the static frictional force can hold. And so from this, we're going to go ahead and take this guy and let's plug him back into our next equation, which is going to be our kinetic. And so we know that the force of friction then will be equal to the coefficient of kinetic friction, which is 0.55, times the normal force, which is still 568.14. And so that means the frictional force on this object would have to be equal to 312.478 newtons. Now, so we have the frictional force, but the question was, what is the acceleration? And so to find the acceleration, we're going to have to find the net force. So looking at things, then we can say in the x direction, which is the direction it's going to accelerate, there are only two forces, FAX and FF. So that means that our net force, I'm going to sort of divide our sections here, which is mass times acceleration, would have to be equal to our FAX force, which is 443.16, minus the frictional force, because it's going to be in the opposite direction. The frictional force we found is 312.478. And this is going to be equal to the mass, which is 50 times the acceleration. Okay? And so in doing this, we can solve this out. If we solve for our acceleration, 443 minus 312, we get that answer here divided by 50. Acceleration comes out to be 2.6137 meters per second squared. If we look overall at significant figures, we still have 1 for this guy right here. And so our acceleration is going to be somewhere in the neighborhood of 3 meters per second squared. And so that would be our acceleration of our rock in this case. So this would be a little more complex case where our original applied force is not parallel to the surface. Just because if it's not parallel to the surface, then you have to take into account changes the normal force, number one, and number two, you can't use the applied force as what you compare with your frictional forces, especially your static frictional force. You have to use the x component of that, which is the one that basically is parallel to the surface. So, one last case, and we'll be done for this lesson. So what we're going to be talking about here is going to be what happens if we're not on a level surface. What's the acceleration of a 50 kilogram rock sitting on a 20-degree inclined surface? US 0.75, UK 0.55, if a force of 450 newtons is applied down the incline. So in this case, we have a nice inclined plane where 20 degrees is our angle here. We have our rock sitting on this inclined plane here. Let's see if I have enough room to do this here. We have a gravitational force downward. We have an applied force, which in this case is down the incline, so our applied force is this way. We have a frictional force, which is going to oppose that, going back up the incline. And we have a normal force, which is perpendicular. It's right up there. Okay, and so this case right here, we asked what's the acceleration. Well, we know the acceleration is going to have to be either up or down the incline, one or the other, or it's 0. So we know that means that since the acceleration is sort of off at a skewed direction, we're going to want to do an axis rotation. And so we're going to take this guy right here. Let's rotate him around by 20 degrees. And so if we rotate him around by 20 degrees, now here's our rock. The normal force is up. The frictional force is off to the right. The applied force is off to the left. And the gravitational force is now angled. And so really we'd want to take this and break it into components. And we have two components here. We have a y and an x right here, and the interior angle in there is going to be 20 degrees. All right, so this is sort of our setup here. All right, so in this case we first need to figure out, is this object moving or not? And to find that, we'll have to find the static frictional force, and to find the static frictional force we'll need to know the normal force. And so to get the normal force though, we have to say, okay, we know this rock is not accelerating up through up in the air. It's not falling through the inclined plane. That means our y forces are going to have to add up to 0, which means that the normal force is equal to the y component of the gravitational force. And so to set this up, we would say, all right, let's find our FG, our components in the x direction. Let's find them in the y direction. We can find the y direction is what we're going to need first, but we'll go ahead and figure them out in both directions. And so the force of gravity here, it's still a 50 kilogram rock. We haven't changed anything to save us a little bit of time. It's still on Earth, so that means 50 times 9.8 is going to give you 490 is going to be newtons, and that 490 times, in this case we're looking for x, that's going to be opposite down here, and so if it's opposite then it's going to be sine, so 490 times sine of 20 degrees right here. You do the math on that and you get 167.59. Okay, newtons. For y direction, it's going to be 490 times cosine of 20 degrees. And so if you do the math on that, that should come out to 460.45. So 460.45 newtons is our force in the y direction. Now, the normal force has to equal that force in the y direction. That means our normal force is going to be equal to 460.45 newtons. All right. So we know our normal force now. Let's go ahead and start figuring out our frictional forces. So for the static frictional force is always less than or equal to mu s, 0.75, times the normal force, 460.45. And so that means that the static frictional force has to be less than or equal to the maximum possible value you could have would be 345.337. Now, let's look and see if our applied force is big enough to overcome that. The applied force in the x direction we found was 167.59. And so you might say, hey, nope, that's not going to work. We're sitting still. But you will have forgotten something. That's that there are two forces that are pointing down the incline. The applied force is not the only one. The other one, sort of in our negative x direction, is we've got our applied force that points down this way. We also have the x component of the gravitational force, and so we're going to have to add those two up. The question is, are those two bigger or smaller than the 345? Because those are both pointing in the opposite direction. They're both trying to overcome that frictional force. And so looking at this, we would say, all right, let's take a look. We have the forces are the applied force, actually the applied force here, which is going to be 450 newtons, plus the x component right up here, 167.59. Is that greater than or less than 345? That's very clearly going to be greater than 345. And so that means this object will accelerate because we have two forces going here. Add them up, we get bigger than this. And so we know we're going to be dealing with kinetic friction. And so let's look at kinetic friction here. And so the kinetic frictional force is going to equal to mu k, which is 0.55, times the normal force. Normal force we already figured out is 460.45. And so that gives us a frictional force of 253.247. If you do the math, newtons. So we have now three forces in the x direction. We know them all now. Going in the leftward direction, which we'll call positive here, we have a 450 Newton applied force right there. And to that we're going to add our next force here, which is the x component right in here, 167.59. And from that we're going to subtract our frictional force, 253.247. And so this should give us our net force. And so if we do the math on that, so adding those up and combining that, we should end up getting 364.34. That's going to be our net force, is equal to mass, which is 50, times acceleration. So divide both sides by 50. And so we should get an acceleration here, 7.286. Significant figure should be just 1 right here. And so our acceleration would be 7 meters per second down the incline. And so that's what we get here. So this would be an example of how we would set up a case of friction on an inclined plane.